In this video, I'll demonstrate some um examples which are based on the work energy theorem. So the first example which you can see on your screen is this a block which is kept at a height of 1 meter is allowed to fall on this roller coaster or inclined plane, anything you can say, and it will jump from this point. It will start from this point A and it will jump off from point B. So we need to find out that at how much distance, horizontal distance, this block will jump and it will fall. So first of all, we need to find out the velocity of this block at this point. So let's suppose this velocity is v. So we can see that the difference of height in these two levels of the block is 0.5. So this block has gone down by a distance of 0.5 meters, and therefore work done by mg on this block will be mgh, mg delta h. Now what that mg delta h I can say that mg is let's suppose m is not given, so m into g is 10 and delta h is half. So this is 5m, and that is equal to the work done by mg is equal to change in kinetic energy of the body. So the change in kinetic energy will be half mv final square, and initial velocity was 0. So it is equal to work done. Work done is 5m, and cancelling m with m, v square is equal to 10. So v is equal to root 10. Now we know that the formula for the horizontal, in fact we can find the time in which it will jump to the ground, and let's suppose this time is t. So this is the time of flight of projectile motion, and it is equal to under root of 2h by g, and this is root of 2, h is half and g is 10. So this time is 1 by root 10. Now this range r can be calculated easily by multiplying this velocity with this time of flight, and hence the range will be 1 meters. So it will fall on the ground at a distance of 1 meter from this point B. Now we move on the next question. In this question, it is given that a bullet of mass 20 kg is fired from a rifle with a velocity of 800 meters per second. And when the bullet has gone past through a wall of mud of 100 centimeter thickness, then the velocity of the bullet drops to 100 meters per second. So we need to find out the average resistance which wall has applied on the bullet. So let's suppose the wall has applied an average resistance of F, and the thickness of the wall D is 100 centimeter, which is 1 meter. Now work done by the wall against bullet is equal to the average resistance F into the thickness of the wall, and this work done against the bullet is gone in decreasing the kinetic energy of the bullet. So kinetic energy change will be, I'm writing this change considering the fact that kinetic energy has decreased, so I'm writing the kinetic energy change as initial kinetic energy minus final. So initial was this 800 whole square minus the final will be 100 whole square. So if we equate these two, then F into D will be equal to half, and mass will be 20, and it is in the gram, so it is 10 to the power minus 3, and this will be 64 and this will be 10,000. So now F into D is 1, and this is 10 to the power minus 2 into 10 to the power 4, and this is 63. So F will be equal to 6300 newtons. So this is the average resistance which wall has applied on the bullet. Now we move on the next question. In this question, a particle of mass 0.1 kg is subjected to a force which is a variable force, and this variable force is changing with the distance x as shown in the figure. We need to find out the velocity of this particle at the mark of 12 meter distance, and assuming that it has been started from rest at x is equal to 0. So this is a very simple question, and we know that the area of fx graph with the x-axis, obviously with the displacement axis, is equal to the work done. So its area A will be equal to half sum of parallel sides, which will be 12 plus 4 into this height is 10. So area will be equal to 80 meters. Now this area will be equal to the work done, and work done hence will be equal to 80 joules. Now from work energy theorem, we know that work done is equal to change in kinetic energy, and given that initial kinetic energy was 0 and final velocity we have assumed as v, so work done will be equal to half mv square minus initial kinetic energy was 0. So it is equal to 80, and this is half. The mass of the body is 0.1, and its velocity v square will be equal to 80. So v will be equal to 160 with a square root, and 1600 in fact, and this would be equal to 40 meters per second. So the correct option will be option number D in fact. Now we move on the next problem. In this question, it is given that a body which is moving at a speed of 2 meters per second, and it can be stopped over a distance of x by a force F. So if its kinetic energy is doubled, then how long will it go before coming to rest? We know a fact that in these kind of cases, when a body is being retarded by a force, then the work done by that force against that body will be W is equal to F into x, where x is that distance in which that body is coming to rest. And in the first case, that body is coming to rest at a distance of x. So this F into x is the work done by that force against that body, and this will be equal to change in kinetic energy, and final kinetic energy is 0, and initially it was, let's suppose it was k. So for first case, in first case the work done F into x will be equal to k, where k was the initial kinetic energy and the final kinetic energy will be 0. But if we have doubled the kinetic energy, then the force and the force is also remaining the same. So the distance at which that body will be coming to the rest, let's suppose it is x dash, and that would be equal to 2k. Now we can see that x dash upon x is equal to 2, and x dash will be equal to 2x. So the new distance over which that body will be coming to rest will be 2x. So the correct option is option number B. Now we move on the next question. In this question, it is given that there is a block which is situated at point A, and this block is sliding on this smooth surface AB. But beyond the point B, when this block is moving on this horizontal surface, then there is some friction present on it. Now due to that friction, this block is moving in a motion of a retardation, and hence it would come to the rest at some point here. Let's suppose this. So this is point C, let's suppose, and this distance through which this block has retarded is x. Now we wonder that which forces are being applied on this block throughout the motion. So when this block is coming down, then mg is also acting in the downward direction, and the distance which this block has traveled in the downward direction is 1 meter. So the work done by mg will be equal to positive, and it will be mgh. Now initial kinetic energy of the block was 0. You can see that we have released the block from rest, and final kinetic energy of the block is also 0. As you can see, that block will eventually come to rest at the point C. So the change in kinetic energy of the block will be 0. Now this work done by mg and another force which is friction force will be acting on this block in BC. So in region BC, friction force which will be acting on this block will be mu mg, and mu will be equal to 0.2 and mg will be 10 newtons. So friction force which will be acting on this block in this region BC will be 2 newtons. Now we can say that when this block will be traveling from B to C, the friction will be acting in the reverse direction. So the work done by friction will be negative, and hence it would be negative, and it would be F into X, and F is 2 Newton. So work done by friction is equal to minus 2 into X. So we need to apply the work energy theorem, and work done by mg plus work done by friction is equal to change in kinetic energy. So work done by mg is mgh, and the value of mgh will be 20, in fact 10. Mg is 10 and h is 1, so this is 10, and work done by the friction will be minus 2x, and this is equal to 0. So 2x will be equal to 10 and x will be equal to 5. So the correct option will be option number A. Now we move on the next question. In this question, there is an inclined plane. I am drawing that inclined plane, and there is a block which is kept over this inclined plane. This block is being released from rest from the top of the inclined plane, and the inclination angle of this inclined plane is theta. The coefficient of friction of this inclined plane is mu is equal to mu naught into x, and it is a variable one, as it is depending on the x, which is the distance from the starting point which the block has moved, this one. So this we have to find out the distance at which this block will finally come to rest. So if we are releasing from point A, and we are assuming that this block is coming to rest at this point, let's suppose this is B and this is C. So the kinetic energy of this block at point A is 0, as well as at point C will be 0. So the initial kinetic energy of the block will be 0, the final kinetic energy of the block will be 0, and the change in kinetic energy of the block will be 0. Now when this block is moving down, and when it is at point B, then the friction force acting at point B will be equal to mu into mg cos theta, where mu is variable. So FB will be equal to mu naught x into mg cos theta. Okay, and the mg sin theta will be acting on this block in the downward direction. So when this block is going down, work done by mg will be equal to the mg sin theta, which is acting along the inclined plane in the downward direction, into the distance. Let's suppose x naught is the distance from point A to C, where the block has finally came into rest. So work done by mg will be positive mg sin theta, because this x naught and mg sin theta are parallel to each other, both acting in the downward direction. But as block is going down, this friction is acting in the upward direction, and the displacement of the block is in the downward direction. So the work done by friction will be negative, and obviously friction is a variable force, so it should be calculated with integration negative minus mu naught x into mg cos theta, and for a small displacement dx, the work done by the friction will be minus mu naught x into mg cos theta into dx. Now for the complete displacement x naught, 0 to x naught, we integrate this, and work done by friction will be negative mu naught mg cos theta into x square by 2, and this is x naught square by 2. So we write the work energy theorem as work done by mg plus work done by friction is equal to change in kinetic energy, and the change in kinetic energy is 0, as initial and final kinetic energies are 0. So work done by mg will be equal to mg sin theta into x naught, and work done by friction will be equal to minus mu naught mg cos theta into x naught square by 2, and this will be equal to 0 because the change in kinetic energy is 0. So x naught from this equation will be equal to this 2 tan theta upon mu naught. So the correct option will be option number A. Okay, now we move on the next question. In this question, it is given that that a block of 10 kg mass is being pulled on this circular frictionless arc whose radius is 10 meter, and the applied force F is constant throughout, and the value of F is equal to 200 newtons. Now this block has started from rest at point A, and we have to find out its speed at point B. Now the radius of this arc is also given us as 10 meter, and we need to find out the speed of the block at point B. So we need to notice one thing, that this force which is acting on this block is constant, and it is 200 Newton, and when the block has started from A, this tension force acting on this block is always pointing towards this point B. So whether the block is at point A or somewhere between A and B, this tension force is always pointing towards this point B. So if we calculate the direct displacement of block from A to B, because the force is always acting towards point B and the force is also constant, so to calculate the work done, we can just multiply this force with this direct displacement AB. So this AB will be equal to R, because this is an equilateral triangle, and R is equal to 10. So the work done by this force F is equal to F into this distance R, and this is equal to F, which is 200, and R, which is equal to 10. So work done by F is equal to 2000 joules. Now when this block has gone up from A to B, it has also ascended some height h, and therefore work done by mg, which is acting in the downward direction, always will be negative, because mg is acting in the downward direction and this block has gone in the upward direction in y-axis. So work done by mg will be minus mg into h. So the total work done, now I can calculate this work done by mg, it is equal to minus, and mg is 10 into 10, and this h is equal to this height r minus this height r cos 60. Now this is r, and the component of r here will be r cos 60, so h will be equal to r minus r cos 60. So r minus r cos 60 is 10 minus 10 cos 60, which is equal to 5, and work done by mg will be equal to minus 500. Now we apply the work energy theorem. Then work done by mg plus work done by F is equal to delta K, change in kinetic energy, and work done by mg is minus 500 plus work done by F is 2000, and the change in kinetic energy will be final kinetic energy half mv square minus initial kinetic energy, which was 0. So this 1500 is equal to half m is 10 and v square, and this v square will be equal to under root of 300. V will be equal to under root of 300, and therefore v will be equal to 10 root 3. So the correct answer will be option number B. Now we move on the next question. In this question, there is a block of mass 1 kg which is moving under the influence of a variable force F. At t is equal to 0, the displacement was 0, and the velocity of the block will be was given to be under root of 20. Now this force is always acting in the direction of velocity, and we need to find out the incorrect options. I am highlighting the word incorrect options. So first of all, first option is velocity of the particle will increase up to 2 meter and then it will decrease. Now if we analyze this graph of force, so we can say that throughout this journey of 6 meters, the force is positive. Force is positive in this region as well as force is positive in this region. So throughout the journey of 6 meters, this force is positive, and the positive force is acting in the direction of the velocity. So the velocity of this particle will always increase till 6 meters. So the option A will be incorrect, and due to the fact that we have to choose the incorrect option, then our correct answer will be option number A. Now the final velocity at point 6 at s is equal to 6 meter will be 10 meters per second. Now we need to check this out, that the work done by this force F will be equal to the area, and the area will be equal to half sum of parallel sides, and this is equal to 6 plus 2 into height. Height is 10. So this work done by F will be equal to 40 joules, and this work done is equal to change in kinetic energy half m v final square minus v initial square. Now this 40 is equal to half, mass is 1 kg, and v final is v final and v initial is 20, root 20, because but I am writing it as square, so it would be 20. So v final square will be equal to 100 and v final will be equal to 10. So this is a correct fact that at the end of the journey the final velocity will be 10, but we need to answer the incorrect options. So option number B will not be the correct answer. Now, thus option number C. The final velocity at point at s is equal to 6 is 4 root 5. So this is not correct, but we have to choose the incorrect one. So C is the answer. And option number D says that the acceleration is constant up to s is equal to 2 meter and then it is negative. So this is wrong, as we have already discussed that force is positive throughout, but the only difference between 0 to 2 meter and 2 to 6 meter is the fact that in 0 to 2 meter the force is constant and from 2 to 6 meter the force is decreasing. So we can say that option number D is also not correct, but it will be the answer which we need to identify. Now we move on the next question.